I thought we would kick things off with a sort of just a quick overview of LiDAR and some observations from the past. I wished I'd have been able to find a few more of the interesting LiDAR point clouds that I've seen through the years, but hopefully what some of my comments will be of use and may perhaps set the stage for the rest of the day. So I've been working with LiDAR now for, probably over 20 years, 25 years. And just a very broad overview, LiDAR is becoming quite ubiquitous. We range from, for example, airborne LiDAR, in this case, an example of a topo-bathymetric airborne sensor. Of course, topo-lidar has been around a long time, since the 90s, perhaps even some prototypes before that. Mobile laser scanning, so mobile mapping units. Here it's on an ATV, but of course we have in the panel Alex from Eagle, who have their sensor on a vehicle. Merging with multi-beam echo sounding, how that laser scanning can go. Of course, terrestrial laser scanning is very popular. Most survey firms have a terrestrial laser scanner now, and more recently we're starting to see drones emerge, both from a topo-lidar perspective and more recently some topo-bathy lidar developments. Here's my pitch to the community. I'd like to see us stop using the capital LIDAR acronym and go to just LiDAR.
Tim,
similarly to as we do with.
Sorry, I got to interrupt you.
Yeah.
Somebody in the chat is saying they can't see your screen. Is anybody else? I'm able to see Tim's screen. Is anybody else having problems with seeing Tim's screen?
Oh.
Everybody.
I see a thumbs
it's
up.
all good. It's all good. Okay, sorry
All
for
good,
interrupting. Yeah. Whoever's having trouble with that, it might be your settings. Okay, sorry,
Yeah.
Tim.
No.
Keep going.
No, that's okay. Alex, good luck with getting that screen up there. I'd like to see us start using LiDAR like we do radar and sonar. We don't capitalize those any longer. However, let's do a quick, what is LiDAR? Light detection and ranging. So we fire a laser pulse, we track the time of that emission of that laser pulse, and we essentially have a receiver that when that pulse reflects back off of a target, we define that time as well. And the range, of course, is the two-way travel time multiplied by the speed of light divided by 2. That gives us our range. Now, what I want you to start thinking about a little bit, and I've tried to draw a couple of returning waveforms down below here. So imagine this is the energy that is coming back from the target. And you'll see they're very different shaped. One is a response that sort of has a broad Gaussian distribution, and I put a line there to say when the time interval meter is going to say, we have now a return. And that could be quite different than a return that has a much sharper, narrower peak. So the reflectivity of the target can sometimes influence the range. Sensors have become much more improved than the early days, but we used to actually see some offsets in the elevation or the range, depending on the reflectivity of the target. Again, just to set the stage for, we're operating in waveforms and waves. And then these get converted into discrete points. Okay, so here's what I want to chat a little bit about. Some LiDAR principles are really, we need to sometimes think back to like the type of lasers we're using and what those lasers are doing. And as I mentioned, these variables have improved over the years, but some things I want to chat about today are laser wavelengths that we're using, and that's going to depend on the targets we're trying to survey, the range at which we're trying to survey them with, and of course the medium that we're passing through, whether it be air or air and water, etc. Other factors with the laser include beam divergence. So how much does that laser beam spread as it's transmitted to the target? The laser pulse width. This is something that the end user may not often think about, but this essentially controls the range resolution of the system. So the ability to separate two targets that are sort of being reflected by that pulse How close can those targets be for us to be able to still resolve them? The laser pulse repetition rate, or the pulse repetition frequency, PRF. And this is essentially how many times can that laser pulse per second. And of course, this influences the point density. And I'm going to show you and talk a little bit about pulse density versus point density. Other factors we're not really going to have a chance to talk about are things like transmit power, eye safety, the receiver optics, signal to noise ratio, and of course, other supporting technologies such as the scan angle mechanism, navigation and positioning, and many of these things ultimately, in addition to the laser, control the absolute accuracy of a LiDAR system. So let's think about wavelengths for a moment. And here we have the classic spectral reflectance curve of water, vegetation, and soil. And we have the old Landsat bands on there. I think I could draw this diagram in my sleep. But what I've superimposed here is the 532 nanometer wavelength, the 1064 nanometer wavelength, and the 550 wavelength. These are very common wavelengths used in LiDAR and laser systems. Some additional ones, 515 nanometers, 865, 905, and then we have our, as mentioned, the other ones. So bathymetric LiDARs are typically operating as green lasers, 515 and 532 nanometers. The standard topographic LiDAR mappers that are out there typically are 1064. Now the terrestrial LiDAR sensors, here 550 and other wavelengths. And these things vary based on things like eye safety concerns, the amount of power, the beam divergence, and of course, the type of wavelength and what we're expecting to hit for a target and what medium we're going through as mentioned. But those are the common ones. Let's keep going and look something at, for example, beam divergence. On the left shows two different lasers being emitted, and we measure beam divergence in terms of milliradians, okay, an angular measurement. So for example, at 1,000 meter altitude, a 0.3 milliradian laser beam divergence will produce a laser beam footprint diameter of 30 centimeters, whereas a 0.7 milliradian beam divergence at that same altitude will produce a 70 centimeter laser diameter footprint. So the beam divergence is something I always want to know about when I'm looking at new data or new products. I want to understand how far that laser beam has diverged at a given altitude or range. If we go to the top diagram, we're looking here at the scan pattern. The one on the left is sort of the old sawtooth pattern, we used to call it, and typically here you had a mechanical mirror that was directing the laser pulse back and forth, and as the aircraft advanced, we produced the sawtooth pattern. That had some issues because of the mechanical movement and the stop and go of the mirror system. Now we typically see a lot of systems that are in a circular continuous motion pattern here, in this case a circular or elliptical laser scan pattern. Now, the idea of number of returns versus number of pulses. It's important for LiDAR users to remember for one laser pulse being emitted from the aircraft, you can have multiple returns. Obviously, we might, in this diagram, we have a first return off the top or near the top of the canopy. We have some intermediate returns through the canopy, and then finally a last return at the bottom of the canopy, in the ground in this case. So thinking about pulse density versus point density are two different things, and we need to be aware of that. Now, I promise this will hopefully be one of the last technical slides I want to show, but the idea of the pulse width and the timing between when the laser actually fires and emits its pulse of energy. The range resolution is controlled by the speed of light, the pulse width divided by 2. So on the top right are showing essentially two returning pulses that are separated by a time, and they're clearly distinguishable between those two pulses. Whereas on the diagram on the top right, we see that those pulses are actually overlapped and therefore may be difficult to discern what is happening there between those two targets. And if we come down to the lower left, there's another example here showing on the far left would be two pulses that are coming back to the receiver and basically look like one broad Gaussian distribution pulse, so that it's impossible to distinguish the two pulses. In the middle diagram, we're starting to see a separation of the two, but we still, depending on the optics and the time interval meter, may not be able to resolve them. And finally, in example 3, we have two distinct returns, so we're able to actually resolve two targets at that level. And if we look on the right, here's some examples of pulse width, and the black being 10 nanoseconds, compared to the bottom being the blue being 1 nanosecond. And even though these may all look very similar to you, if you look at the black and you see how broad those pulses are, how wide the wavelength is of the pulse, and then you look down at the blue, you'll see how much narrower they are. So, for example, today, systems that have a pulse width of 2 nanoseconds have a range resolution of 30 centimeters. We used to operate an Optec ALTM system that basically had a dead zone of about 2 meters. We couldn't resolve targets that were within 2 meters of each other at the waveform level and therefore at the point cloud level. So those were important things to think about. Let's now go and just talk briefly about how the point density and as a result the pulse repetition frequency has changed through time. These are some diagrams that I've used through our experience with working with LiDAR back from the 2000 to the early 2004. You'll notice on the left here, diagram A, the original LiDARs we were working with, this was an ALTM system, 5,000 hertz. So the pulse repetition frequency was 5,000 pulses per second. And then, not too long after that, we had 10,000. And then within a few years, 30,000. Eventually, when we had our ALTM 3100, it was capable of 100,000 pulses per second. Today, we're now into the megahertz. We can have systems that can pulse over 1 million points per second, which is quite amazing. And what are the implications of point density versus pulse? So this slide is a little bit complicated. Let's start at the bottom of the slide first. Here I'm showing some of the Nova Scotia provincial data, GeoNova, that was collected by Leading Edge Geomatics. This was collected in 2018 using a Regal topographic LiDAR sensor. And we have some ground control points in white. And we see the point cloud of a cross section here. And I guess what I'm also pointing out on this slide is that the dense shrubbery, the dense reeds and grasses adjacent to this riverbank, the LiDAR is not going to get through to that and get to the ground. Part of that is related to this pulse width idea and being able to resolve targets, and secondly, just the density of that grass. So we can see, for example, we have about a 70 centimeter bias between a DEM produced and compared to the real ground. The DEM is biased too high when we survey in these types of conditions. If we look at the top slide, that shows some data collected from the NSCC sensor, including a topo and a bathymetric scanner in 2019, and we see the same ground control. We have the same issues of not being able to penetrate as maybe a little farther, but not quite as, but incredible density. And that included both the topographic laser and the bathymetric scanner. And when we look at the bathymetric scanner, there we're a little closer than the GeoNova data to the actual ground truth. And just continuing on that, if we look, for example, in terms of forest metrics, the original data in 2018, very good point density, but in 2019, we were able to surpass that with an incredibly dense point cloud. And if we look at individual trees on the right-hand side, quite a contrast between the original GeoNova data and what the AGRG data could show. And here we have our different GeoNova on the left, the bottom set of slide graphics, the bathymetric scanner only, and the bathymetric and the topographic scanner. And then finally, using these additional synthetic points that don't really have time to talk about today. So LiDARs are everywhere. So we're familiar with airborne LiDARs for mapping topographic. We also have airborne for topo-bathymetric, terrestrial LiDARs for close range, whether it be indoor or outdoor using tripods, factories, plants, things like this. Mobile mapping, growing technology for mapping municipal infrastructure, typically street furniture, other types of power lines, power poles, etc. We even have satellite LiDARs. We've got some completed missions, being the ICESat and the CATS on the International Space Station. We have some current missions up there listed, and then a few future missions planned as well. So if you're interested in what's happening on the space satellite side, just have a look at some of these things on the internet. Now, more recently, drones are becoming LiDAR equipped. We've seen quite an advancement in topo-lidar drone mapping in the recent years, and now we're beginning to see topo-bathy being pushed out into that drone environment. Of course, we hear about LiDAR on autonomous cars, and you can even have LiDAR now on your phone or tablet. So it is becoming quite ubiquitous. There are numerous applications of airborne LiDAR, too many for me to go through today. But forest inventory, corridor mapping, power lines, rail, roads, geological mapping, oil and gas, volume estimates, cut fill, city mapping, a huge effort in Europe looking at digital twins of the city environment and the built environment. Of course, on the natural resource side, watersheds, streams, floodplain mapping, and we're going to hear a talk next from NRCan on how that activity is supported. This is a bit of an old slide, but just showing you the amount of terrestrial laser scanners out there. And I would say now that your traditional survey companies doing land surveying often will have a terrestrial scanner in their inventory for doing work. These model numbers are probably now equipped with some newer products. I'm going to talk now a little bit about topo-bathymetric LiDAR mapping. That's my area of specialty. Here, NSCC owns the Chiroptera 4X system from Leica Geosystems. It's equipped with a near-infrared and a green laser. The green laser on the left, we see the waveform reflected from the sea surface and then eventually the seabed. The near-infrared laser only surveys the land and the water surface. It typically doesn't penetrate the water column. And here, there's two different distinct things with regards to the beam divergence. The near-infrared laser has a narrow beam divergence, whereas the green laser has a wider beam divergence. This is a bit complicated, but it very broadly takes you through, first we plan the flight, then we go out and actually conduct the survey. We have a raw trajectory of the inertial system on the aircraft and the GPS. We process that trajectory using either a real or a virtual base station. Once we have the trajectory processed, the waveforms can be converted into point clouds, or some systems build the discrete points on the fly. That point cloud can now be exported. We go through a process of classification refinement, and then finally, once we have good classified LiDAR data point clouds, we can build different raster products, do further analysis, including extracting thematic layers from the raster data, and then finally perhaps push that out to web services. So there's kind of a broad scheme of the range of things. And here's an example of a trajectory. You can see where the aircraft on the top right is making its turns, and then you can actually see where it's collecting data, where we have the very tight parallel lines for a given survey. And on the left side just shows an example of where we've been flying. These data need to be updated, but over the past 10 years or so. Just looking at the raster products, so on the far left here we have our elevation data, color-coded from bathymetry in blue up to land in the greens through the reds. We have our LiDAR intensity map showing us the amplitude of that reflected signal. And then often we have an aerial photo captured at the same time. This system has two cameras, an RCD30 60 megapixel camera and then a quality assurance camera. We'll often do ground truthing, especially when we're looking at mapping the benthic habitat of the seabed to understand what's there so we can relate it to the intensity and the aerial photo. And we can produce a benthic habitat map. Often people are interested in things like submerged aquatic vegetation. We're typically up around the 80 to 90% accuracy range with doing that. I want to just go back to this waveform for a moment. And there's a couple of key things here to note. One, in the bottom diagram, you'll notice that there's a waveform that actually didn't get detected. So there's still research to be done on improved detection of actual real targets in the waveform. Secondly, currently the peak amplitude or the peak intensity is used to produce the intensity points, the intensity values of the point cloud that then can be gridded to a raster. We could also look, and systems are starting to evolve and capture more of this information about the reflected waveform, the area under the curve, the shape of the waveform, kurtosis, these different types of metrics that are associated with the waveform, and sometimes these can provide us more information than simply the peak amplitude of the reflected signal. We can then also normalize by depth. I'll talk about that in a little bit here. Beam divergence, I mentioned this already. In this particular sensor, the topo-lidar is 1064. It has a 0.5 milliradian beam divergence. Quite different than the bathy laser, which is 515 green, has a 4 millirad beam divergence. And it has a pulse width of 2.5 nanoseconds, so it can resolve targets within 35 centimeters of each other. So at a typical survey altitude of 400 meters, the topo laser has a 20 centimeter beam diameter footprint, laser footprint, whereas the bathy laser has a 160 centimeter footprint. Now, with bathymetric lidars, it's important to consider the effect of moving that laser pulse moving from air into water. So the speed of light is much slower in water than it is in air. In air, we assume it's a vacuum, but it's slower by about 75% as it moves into water. This change in the speed is actually what causes the refraction angle, so a slight change that's depicted on the diagram there. So we make use of the near-infrared laser to measure that water surface in order to be able to back calculate knowing where the water surface is and the geometry of the incident beam, the angle of incidence, in order to compensate for the beam divergence and the adjustment in the speed as that system moves, as that pulse moves through the water column. So very important to know the water surface. Here we did a little experiment showing the top profile here shows you the height, the elevation versus the depth. And we have multiple surveys over the years that all line up quite well. And here is one survey where we did not compensate for the diffraction angle or the change in the speed of light. And you see that it gets artificially too deep because it's assuming one speed of light and it should really be compensated at 25% less. So, and for example, over a 10-meter depth, the error is 2.5 meters, so about a 25% error. So, and of course, that gets progressively worse with more depth. So important that these things are compensated. Now, let's look at LiDAR intensity. And here I mentioned that we have the RCD30 camera. This shows you all of the intensities that were captured in a scene above the water line. And then once we go into the water, you'll see the signal drops to zero very quickly. If we look at the red band of that camera system, it's not as broad as the near infrared, and we do get a little bit of information in the water. In the green, it's somewhat similar, perhaps an even clearer signal of the green information. And then moving over to the blue, very similar looking to the green. Now, if we compare that to the LiDAR, here we have a very tight set of information on the near infrared laser, and then it stops. No penetration through the water column. And we have a very interesting pattern in the green laser, 515 nanometers. And we broaden that out, we see that there's actually the vegetation forms that cloud in the center, and we have more sand defining that bottom. I'm running out of time here, so I only want to talk briefly here about water clarity and the fact that we need clear water for these bathymetric systems to work. I'll draw your attention to wind speed up here. These light blue bands represent daylight hours. So on day 2, we had wind and a wind event come in and stir the water up. Here we're looking at the solar radiation on the land. Here we're looking at it underwater. And what's important down here, we're also measuring the turbidity. And this red line represents where the turbidity increases. This shows us a series of measurements of light sensors underwater. So you can see before the turbidity event, we had a good response of the light sensors, but when the water got turbid and dirty, as depicted here on the red values, the turbidity, the amount of light reaching these sensors dropped down. And then it managed to rebound when the water cleared up again. And for example, if we were to plot the water depth of these sensors compared to the amount of light, it's an inverse relationship. The deeper the sensor, the less light is getting there. The shallower the sensor, more light is getting there. Now, it's important to understand that light exponentially decays as you move through water. So it exponentially decays with depth. And here's some empirical data of these different sensors plotted, and we can calculate an equation where we're looking at the exponential diffuse attenuation coefficient. This is related to the water column itself, which can change rapidly over time, as I've just demonstrated. Now, when we think of the beam itself, we have this beam divergence issue we talked about. Now, once it starts to go into the water column, that beam starts to scatter and spread out even more before it finally is reflected back out and back up to the target. So one must consider that and think about that. Now, let's look at some practical data. Here is the original LiDAR reflectance, or the intensity data, which is a combination on the land of the near-infrared laser and under the water, the seabed captured by the green laser. You can actually see from flight line to flight line. So the first thing we do is tighten that up and normalize that, and that's what we see on the bottom. And you see it can be easily compared with what's going on in the air photo, where there's sand, where there's vegetation. Here's an example of that exponential curve again. And what we've done here is there's the original intensity on the top, the depth on the bottom, and we've sampled along different depths, ideally trying to stay within one cover type like sand. And what we can then do, we can plot that, and we can see there's that exponential decay again of the observed intensity at depth. We can develop an inverse model for that, and then apply that equation and get a result of what we call depth normalized. So the new intensity is a function of the original intensity and the depth. And here's an example of what the original intensity looked like. These dark areas, they could very well be something reflective like sand, but the fact that they're deeper makes them appear darker because of the loss of the energy. We can compensate for that through this depth normalization. So original and depth normalized. We can actually even apply that same technique if we have the detailed depth to passive data like the aerial photo. So we can see a much more sandy bottom. And with that, we can then make better benthic habitat maps, such in this case of eelgrass. This is what eelgrass actually looks like on the seabed. And there's where we can map it all out, in this case using the LiDAR and the aerial photo. So this has been published in a few papers. These are available. I want to quickly move on to spectral, multispectral LiDAR and the idea of wavelength and intensity. The Optec Titan was a full 3-band wavelength system, 532, 1064, and 550, those wavelengths we talked about. And there's a composite image on the right showing that. We've done something similar with our 2 bands. There's the green reflected laser pulse, a little saturated. There's the near infrared. And we've simply then done a ratio of the green over the near infrared. And we can then project those into the red gun, the green, and the blue to come up with this composite image. So now we're actually seeing different colors representing different cover types that the LiDAR is picking up. And if we go in and look a little closer here, we see the roads in yellow. The power lines are really showing up, and that's partly because of the wide beam divergence of the green laser. Picks up that power line very well, in fact, better than the topo laser. A couple of other things regarding how the beam spreads out in the water, and I'm going to move along here. We did an experiment where we put cubes down, 1 meter by 1 meter cubes at different depths and painted them different colors and looked at those effects. Essentially, the long and the short of it is the deeper an object is, the bigger it appears. So for example, if you look on the lower right here, we see that at 3 meters depth, that cube appeared to be about 1.6 meters across, and we know it's 1 meter. And if we move the cube even deeper to 5 meters depth, the cube appears a little larger. This is because the beam is fanning out when it goes underwater, and part of that beam will catch that edge of that cube or the top of the cube and come back and appear to be larger when it builds the actual point cloud. So these are things to always consider. Here is a last slide on the recent push for topo-bathy LiDAR and drones. Now, Regal have had their VQ840GL for a while. It's a green-only laser. It's greater than 10 kilograms. Then we have Lightwave has their Edge sensor. It's about 5 kilograms, green-only laser as well. There's a new one on the market called TDT-Dot green from Amuse Oneself, and it's a little lighter, 3.6 kilograms. Yellow Scan has recently announced the Navigator, and it's green only as well, 3.7 without battery. So a couple of comments I'll make on these. My colleagues at College of the North Atlantic have the Lightwave Edge sensor, and they've had quite a few issues with it. So sometimes being the early adopter, you unfortunately have to pay the price as the technology evolves. So undoubtedly, as these systems evolve, they'll become better, more efficient, and hopefully lighter. You need a large drone in order to fly these topo-bathy LiDAR sensors because of their weight. And the other challenge with bathymetric LiDAR is you require more power than you do with a typical topo laser. So as a result, the increased weight, the bigger drones. And the other thing I notice here is so far we do not have any infrared lasers for the water detection. Now, mostly these are for doing fairly shallow water surveys because of these power issues I discussed. So as this evolves, if we start getting into deeper water, we definitely really want to tighten up that water surface issue. It's going to be interesting, and I definitely want to follow this and keep abreast of that technology. So I want to wrap up. Think always about the laser properties when you're thinking about this stuff. Wavelength, beam divergence, pulse width, pulse repetition frequency. All of these have an impact on what that point cloud is actually measuring and the accuracy and the precision of it. Point density is rising. Obviously, just like computers, we're getting higher point density. Pulse width is shrinking, so we're making the systems more precise. Wavelength and beam divergence still affect the target detection. Did not discuss things like navigation, virtual GNSS, IMU miniaturization, but these are all great things for our industry. It's now available on phones, ubiquitous. When we were mapping the water, we need to consider the light, change in the light. So I'll wrap it up there, and I'll now go and see if we have any Q&A questions.
Tim, can you tell us about what's currently the most interesting project that you're doing in LiDAR with the AGRG, or one of your team members is doing? Can you tell us a little bit about what's going on there?
We mapped Sable Island this year, which was quite interesting. And even at flying at a high altitude for a topo-lidar survey, an aerial photo, we were actually getting bathymetric returns, which is quite interesting because normally we're flying at a much higher higher altitude or a lower altitude to get bathymetric returns. So that was kind of interesting and neat. One thing that we're doing lately, and I presented this at the different Go Geomatics events, is really starting to map rivers. And I'm sure our colleagues at NRCan will talk about mapping rivers for improved flood mapping projects. And I know NV5 and Sven have done some really great work mapping rivers for flood mapping support. We've actually been doing research looking at things like fish habitat and fish passage with the bathymetric LiDAR, giving us time of flight water depth maps. And then from that, using it to do hydrodynamic modeling to simulate, say, drought conditions when that water level is going to get lower in the river. Because a river's on a gradient, you need to induce a hydrodynamic model as opposed to more simpler GIS bathtub approaches. So that's an area that has us very interested now, and we're working with some First Nations groups, and they're really the boots on the ground trying to restore some of these rivers for improved fish habitat like the Atlantic salmon, which is an endangered species. So that's one area that's of interest to us. Of course, we're pushing the boundaries on drones with the Ultim multispectral scanner linked in with the DJI L2 and the thermal sensors as well. So it's quite exciting on the drone front as well. Did you build those white cubes for the underwater? And yes, we did build those. They're essentially we built a few of them ourselves, and then we had a contractor build them to that 1 meter specification. They're built with wire mesh, and to make them solid, we put sort of building wrap, Tyvek as an example, around them, and either painted it white or painted it green, and of course had to cut some slits. Otherwise, they would be floating cubes, and we wanted to sink them. So, great question.